Okay, let's today start with the valence bond theory. Valence bond theory. Okay. This theory was to explain the covalent bonding. Okay. This explains the covalent bonding. Okay. And this theory is based on the wave mechanics. Okay. Means what? Electrons are found in the orbitals. Means electrons are like waves. Okay. So they are found in the orbitals. So the first let's see the what is the valence bond theory. Okay. According to valence bond theory, the covalent bond is formed when the half-filled valence orbital of one atom overlaps with the half-filled valence orbital of the other atom. Understand? The covalent bond is formed between the half-filled valence orbital of one atom with the half-filled valence orbital of the other atom. Okay. For example, let's see with hydrogen. Okay. There are two hydrogen atoms here. Okay. What is the electronic configuration of hydrogen? 1s1. Okay. So its orbital is like this. Okay. 1s1. 1s1. See, so there should be the first point is there should be half filled. Okay. Half filled valence orbital to overlap. Second is what? The electrons in the half filled valence orbital must have opposite spins. Okay? They must have opposite spins. So this is upward, this is a downward. Okay? So when they have opposite spins, they can overlap. So what happens during the bond formation? The half-filled orbitals overlap and the opposite spins of the electrons get neutralized. That's what happens. What will happen here? This 1s will overlap this with this 1s. Okay. So H of one H atom and this is for the other H. Both of them will overlap. Okay. And they will form H2. So this is by the overlapping of the orbitals. Okay. Greater the extent of overlap, stronger is the bond formation. Okay. Means what? Achha, overlapping should not be more than 50%. Okay. It is always less than 50%. So greater the extent of overlapping, more is the bond strength. Okay. So we can say like this, extent of overlapping is proportional to the strength of the bond. Okay. Proportional to the bond energy, inversely proportional to the bond length. Okay. Are you getting me? The extent of overlapping. More the extent of overlapping, more is the strength of bond, more will be the bond energy. And the bond energy will be more, the bond size will become less. Okay? Bond length will become small. Understand? Okay. What happens if there is more than one unpaired electron? If an atom possesses more than one unpaired electron, it can form more than one bond. Okay? More than one or unpaired electron in orbital, more than one bond can be formed. Okay. So see, first and very important point I told you that only the half-filled orbitals participate in bonding. Okay. If the electrons which are paired in valence shell, okay, can it participate? No. Okay. So electrons which are paired in the valence shell cannot participate in bond formation. Okay. However, in an atom, if there is more than is one or more vacant orbitals present, then these electrons can unpaired and participate in bond formation. Okay. Are you getting me? If there are some vacant orbitals are there, okay, and some are filled, so then the filled or by filled electron will shift to the vacant to make the everyone half filled. Okay. Let's see example of BF3. Okay. We'll see example of BF3. Okay. What is the electronic configuration of boron? It's 2. Okay. 1s2, 2s2, and 2p1. Okay. And fluorine is 1s2, 2s2, 2p5. p5. Okay. Atomic number is 9. Okay. How the orbitals, how the bond between boron and fluorine will form. Okay. Let's see. For boron, it is okay. The inner orbital 1s will not participate. Okay. We will not bother for the inner orbital. Okay. So this is a 2s2 and this is 2p. Okay. There are 2 electrons in s and 1 electron in p. Okay. And in fluorine, it has 2s2 and 2p5. Okay. 1, 2, 3, 4, 5. So what happened? Here there is 1 boron and 3 fluorine atom. Correct. And boron has 1 unpaired electron, 1 unpaired shell only. And fluorine also have 1. But 1 boron has to make bond with the 3 fluorine. Okay. So it had to accommodate 3 electrons. Okay, of 3 fluorine. Okay. So what will happen? One of this electron will shift to this. Now there will be orbitals we have. Okay. It will become like this. Now we will have 3 unpaired electrons. Okay. 3 half-filled orbital. And now this 3 half-filled orbital will accommodate this 1 electron. With paired with the 1 unpaired electron of the fluorine. Okay. And thus make the 3 bonding. Okay. So this way we can make a chemical covalent bond. Okay. Okay. We will see first the types of bond. Okay. Depending upon the overlapping of the orbitals. Depending upon the overlapping of the orbitals. Okay. It is of 2 types: sigma bond and pi bond. Okay. On the basis of this, okay, we have 2 bonds: sigma bond and pi bond. Sigma bond is formed by the axial, by the head-on overlapping. Okay. Like this, 1 orbital and 1 orbital by the head-on orbit overlapping. And pi bond is formed by the lateral or sidewise overlapping. Okay. Let's first we know that the shapes of the orbital. Okay. The shape of the s orbital is spherical. Okay. This is the s orbital. P orbitals, it is dumbbell shaped. Okay. It is oriented in directional. Okay. Px. Okay. It is like this. Then we can say the P, Y, okay, and this is the PZ, PZ axis, okay. And D is the double dumbbell. D is the double dumbbell. This is the D, okay. So let's see the sigma bonding. Sigma bond is formed by the overlapping of the orbitals in sidewise, matlab head on. It is also called the head on orbital. Or we can say axial overlapping. Okay. First is the sigma bond. Okay. This is also called, this is the because of axial overlapping. Yeah, one more thing. Okay. We have seen that the overlapping takes place between the orbitals having opposite spin. Okay. But it also takes place with the same sign, between the same sign. Okay. Right now we have seen that okay, this is the, if this is s orbital, okay, and this is s orbital. So both should have a plus sign. Okay. So overlapping takes place between the same sign. If there are orbital axial overlapping between the px and px, okay, so it should be p. This is the p orbitals overlapping. Okay, so this should be plus. Okay, so overlapping takes place between the same sign. Okay. First, we'll see types of a sigma bond. Okay, means sigma bond takes place between one s and one ss. Okay, one s and one p, sp, and p and p. Okay, two p orbitals. Okay, sigma bond could be between s and s orbital. I think between two s orbitals. Okay, it could be between one s and one p orbitals. Okay, and it could be between two p orbitals. Okay, ss, sp, and pp. First, we'll see the ss or ss overlapping. Okay, we'll see what, we'll take an example of H2. Same, this is H, okay, plus this is the other atom of H. Okay, both of them will overlap like this, and they will form H2 molecule. Okay, are you getting me? PP orbital, PP overlap. Okay, as I told you, there's the overlapping should take place between positive and positive sign. Okay, actually orbital is what? Orbital is the place where the most probability of finding the electrons. Okay, so somewhere it's like a wave mechanics, waves. Okay, so somewhere plus and somewhere minus. Okay, we'll take example of F2. Okay, two molecules of F, the configuration is 1s2, 2s2, and 2p5. Okay, other molecule 1s2, 2s2, 2p5. Okay, so only the, okay, we'll see with this is px, py, and pz. Okay, this is 2s. So pz and pz are unpaired. 2s, 2px, 2py, and 2pz. The overlapping will take place between the pz and pz. Suppose this is the z-axis. We'll take this z-axis. Okay, z-axis, and this is the z-axis. Okay, this is the pz, and this is the pz. Okay, overlapping will take place between this pz of one fluorine atom and pz of the other fluorine atom. Okay, so how it will overlap? It will overlap like this. Okay, this is the pp overlapping. Okay. Next type is sp bond. sp sigma bond. Okay, overlapping between the s orbital of one atom and p orbital of the other atom. Okay, this example of with the example of HF. Okay, HF, HCl, HBr, anyway. HF, H has 1s1 and fluorine is same 1s2, 2s2 and 2p5. Okay, so this is the s. Okay, this is s orbital of hydrogen. Okay, and this is the 2pz. Okay, 2pz orbital of the fluorine. Okay, they are overlapping between these two and it will become like this. Okay, sp sigma bond. Okay. So, and now the question could be asked like this: which bond question? Question here can be which bond has more bond energy? Okay, which bond has more bond energy? Or it could be like this: which bond has least bond length? Okay, we have seen the more the overlapping, more is the bond strength, more is the bond energy, and lesser is its bond length. Yes. Okay, so it is given here HF, HCl, HBr, okay, and HI. We have to find out which bond has more bond energy. Okay, how will you find out? See, overlapping will be more. We'll see first N. N is what? N is what? N tells the number of shell. Okay, means what? If N is lesser, okay, it is close to the nucleus. Okay, close to the nucleus means more bond energy. Okay, more closer to the nucleus, more bond energy. So what is the overlapping here? One in between H and F. Okay, it is between 1s and 2p. Okay, the last electron, the last vacant orbital is in 2pz. We have seen, na? It is a bit overlapping between 1s and 2p. In HCl, it is overlapping between 1s and 3p. Okay, in HBr, it is overlapping between 1s and 4p. And in HI, it is between 1s and 5p. Okay, so lesser the number of n, okay, more closer to the nucleus. Okay, yes. So how now we can find out? We can say which has more bond energy. Obviously, this has HF has more bond energy than HCl, then HBr. Okay. So questions used to come like this. Okay, you maybe you have to arrange according to the bond length, according to the bond energy. Okay. So this way you can find out.
So we'll have the least bond length.
This least bond length. Okay. More bond energy, least bond length. Okay. Less bond energy, more will be the bond length. Okay. So this we have seen on the sigma bond. Sigma bond which means axial overlapping. Okay. Head on overlapping, we can say. Now we'll see the PP overlapping. Sigma bond between SS, SP, and PX PX. Now we'll see the PP overlapping. Means pi overlapping. Okay. Second is the pi overlapping. Pi overlapping means what? Means it can be said parallel overlapping.
Okay. Yes.
Parallel or sidewise overlapping. Okay. Hmm? Valence bond theory. Valence bond theory. Valence bond theory. Valence. मुझसे पूछ ली आगे tell me. Okay, now for this we'll take example of O. Okay, O2. Okay, one molecule, one atom of O and with other atom of O. Okay, the configuration of O2 is O is 1s2, 2s2, 2p4. Okay, same 1s2, 2s2 and 2p4. Okay, now let's fill its orbital. Is 2s2 and 2s 2p. 1, 2, 3, 4. Okay, and 2p. 2, 3, 4. Now see, this is the x-axis, this is p y-axis and z-axis. This is x-axis, y-axis and z-axis. Okay. Now there will be the structure should be like this. Okay. So one overlapping is head-on overlapping, axial overlapping. Okay. Between suppose this is the pz. So between pz and pz. Okay. There is a head-on overlapping. Okay. But py and this is the py. Okay. It also has one unpaired electron. So their overlapping will be like this. They will form overlap in this way. Understand? So this is called pi bonding. This is the sigma bond. This is sigma bond and this is the pi bond. Okay. So pi bond formed by the lateral overlapping. Okay, sidewise overlapping. Okay. Next, we'll see one example of nitrogen. Okay. This is nitrogen. You know there is triple bond. How? Let's explain this. Okay. We'll take two atom of nitrogen. Its electronic configuration is 1s2, 2s2 and 2p3. Okay. 1s2, 2s2, 2p3. Okay. Its orbital will be 2s and 2p. Okay. 1, 2, 3. 2, 3. Okay. Now how they will overlap? Okay, this is x-axis, y-axis, and z-axis. This is px, py, and pz. Okay, you can take axis anywhere. It's not necessary that this is x-axis, this is y, this is z. Okay, any axis anywhere. Okay, so this is one side by one head-on overlapping, axial overlapping. Okay, it one form sigma bond, px and px. Okay, one sigma bond. This is py and py. Okay, this is the py one sidewise overlapping. Okay, and this one pz and pz. Okay, this is py and this is pz. Okay, this is px. Okay, py and now pz. Okay, now this will overlap. This pz and pz will overlap. Okay, overlapping between px and px is head on. Okay, overlapping between py and pz and pz is sidewise. Okay, so what happens here? One sigma bond and two pi bond. है ना? This is one sigma bond and two pi bonds. So the N2 molecule has one sigma bond and two pi bonds. Yes.
This one, the zero, it's first zero, two is, and then here is it only two p. I didn't get.
What?
I didn't get this part.
You didn't get this part. Okay. See, this is the configuration of nitrogen. Okay. 2s2 and 2p3. Okay. S is all filled orbital with opposite spins. No problem. P has three orbitals and three half filled orbitals. You can say three half filled orbitals. Same other and N also has three half filled p orbitals. Okay. Now they have to overlap with each other to make the bond. Okay, so px, they are the orientation of the p in z, x, and y axis. X, so this is x axis, y axis, and z axis. Okay, so overlapping between px and px. Okay, this is px axis. The px of the one end overlap with the px of the other end. Okay, and form sigma bond. Py of the one end and py of the other end, this sidewise overlap, form one pi bond. Okay, and pz of the one end and pz of the other end molecule. Okay, again sidewise overlap and form the other pi bond. Okay, so between two n molecule, between two n atoms in the molecule, the one sigma bond and two pi bonds. Okay. Understood? Yes, ma'am. Okay. So we are now able to find out the number of sigma and pi bonds. Okay, if the molecule is given. Now the question here is find the number of sigma bond and pi bond in H2O. Okay, C2H2 NH3. Okay. Now the question here is find the number of sigma bond and pi bond in H2O, C2H2, and NH3. Okay. How will we find? Let's see. So what have we have seen? If there are a sigma bond, one sigma bond. Okay, one bond means one sigma bond. If there are two bonds, double bond means one sigma bond and one pi bond. If there are triple bond, means one sigma bond and two pi bonds. Okay, double bond, one sigma, one pi. Triple, one sigma, two pi. Okay, so first we have to draw the structure of H2O. Okay. Okay, this is the structure of H2O. Now tell me, how many sigma bonds and pi bonds are there?
One pi bond.
Only single bond. How many sigma bonds? One, two. How many sigma bonds in the molecule? Two sigma bonds. Okay. You have to calculate the number of bonds to find out the sigma bonds. Okay. You have to draw the structure. Then you have to calculate the number of bonds. So how many sigma bonds are there? Two sigma bonds. Okay. In C2H2. In C2H2. Okay. Yeah. First of all, we have to draw the structure. How will write the structure? Now calculate the number of sigma bond and pi bond. First of all, calculate the number of sigma bond. 1, 2, 3. 1, 2, and 3. Yes. Okay. 3 sigma bonds. Pi bond? 2. No. 1 and 2. 1 and 2. Okay. Okay. 2 pi bonds. Okay. This way you can answer the question. Now you have to find out the number of sigma bonds and pi bonds in NH3. Okay. How will you find? First, write the structure NH3. Okay. Yes. Number of sigma bond? 3. 1, 2, 3. Pi bond? 3. 0. No pi bond. Okay. And yeah, one more thing. Overlapping is more in sigma bond than pi bond. Okay. Obviously, overlapping in sigma bond is, suppose this. Okay. This way. This is more overlapping than this way. Okay. So overlapping in sigma bond is more than pi bond. Pi bond again. Pi bond again. Pi bond? Rotate pi bond. Rotate pi bond in a sheet. Pi bond you want to see? Yeah. Okay. This? No, but this one. Okay. Okay, see. Okay, then so we have seen the valence bond theory. Okay, it could explain the formation of covalent bond. Okay, by the overlapping of the orbitals. Okay, in case of simple molecules like H2, F2, HF, HCl, and all that. Okay, or between O2 and NH and N2 like this. But in some cases, okay, could not explain well. For example, in BEF2, okay, in BEF2, okay. What is the configuration of BE? BE is 4. 1s2, 2s2. Okay. Fluorine has fluorine is 1s2, 2s2, and 2p5. Okay. So one beryllium atom, okay, combines with bond with the two fluorine atom. Okay, BeF2. So configuration we will show that 2s, okay, and this way. Sorry. Okay. So 2s2, okay, and 2p0. It has 2s2 and no electrons in the p. 2p0. Here, this is 2s2 and 2p5. How there will be the overlapping between these two? Okay, this cannot be explained by valence bond theory. Okay, for that a new concept, new term is introduced: hybridization. Okay, so to explain this type of overlapping, okay, yes, there is hybridization. Okay, hybridization. What is the hybridization? It is the mixing of the valence orbitals. Okay, mixing of the valence orbitals of same atom. Okay, and recasting them into equal number of new equivalent hybrid orbitals. Okay, new orbitals is known as hybrid orbitals. Okay, hybridization means what? Mixing of the valence orbital. We will mix the 2s and 2p and make the new orbitals having equivalent energy, and these are called the hybrid orbitals. Okay, after that they will overlap, intermix. Okay, so it is called as, okay, let's see, beryllium. Okay, beryllium is having 2s and 2p. Sorry, 2s and 2p is 0. Okay, so what will we do? We will excited it. Okay, excited in excited state. Okay, it will, this electron will come to the p orbital. Okay, so it is called an excited state. In excited state, what will happen? Beryllium has now okay, now this electron is comes to this 2p. Okay, 2s1 and 2p1. Then now we can intermix them like this. Okay, okay, this way. And this is called the sp. 1s and 1p. The sp orbital. Now it can make bond with the two fluorine atom. Okay, sp, this is boron, sorry, beryllium, and we have two fluorine atoms. Okay, one fluorine and other fluorine. Okay, this is one and this is other. Okay, so one electron will accommodate here and one, sorry. Okay, one will accommodate here and one will here. Okay, thus forming the two bonds with beryllium,
Okay.
BeF, and one sp with this p orbital of fluorine and this one sp with the orbital of fluorine. Okay. So what type of hybridization here is sp. Okay, new hybrid orbitals are formed, which is called as sp orbitals, because it is from one s and from one p, so it is called sp. What will be the structure here is for sp? Okay, yes, and the hybrid orbitals is shown as the two lobes, with two lobes, one smaller lobe and one bigger lobe. Okay, and the structure will become like this. This is sp for sp. This is 180 degree, and the structure is called as linear. Okay. Are you getting me or not? Little bit confused. Okay. First we'll
Why there is small in the.
Okay. First we will see what is hybridization. Okay. Then we'll go with the examples. Actually, hybridization is the intermixing of the orbitals.
Yes.
Okay. To make the orbitals of equivalent energy. Understand? And these are called the hybrid orbital. Okay. Take examples of like something. You have three black colors clay and one green color clay. Suppose. Okay. So you have to intermix. First you will mix all them, and then you will make they are all together four orbital, three black color and one green color. When you will intermix it, okay, and again you have to make four. So now again the balls of clay will be four, but all the four balls will have the property of both black and green.
Yes.
Okay, same thing happens here. Same way, the s orbital and p orbital, okay, they intermix, and the new hybrid orbitals will have the characteristic of both the s and p. Okay,
Yes.
and it is called sp. If one s and one p orbital is mixed, it is called sp. One s and two p, it is called sp2. One s and three p as orbitals, it is known as sp3. Okay. So for the hybridization, okay, there is there are two conditions for hybridization. Okay, orbitals should belonging to the orbitals which are going to hybridization should be of the same atom. Okay, hybridization occurs between the same atoms. Okay, same atoms orbitals can participate in hybridization. Okay, next orbitals having nearly same energy can undergo hybridization. Okay, orbitals having nearly same energy can undergo hybridization. For example, 2s and 2p. Okay, these two orbitals can undergo hybridization. Okay, and but not 3s and 2p. Understand? This will make hybrid orbitals. This can make, but not the 2p and 3s. The orbitals having nearly same energy. Nearly same energy undergo hybridization. Okay, and they form the hybrid orbitals of equivalent energy, of same energy. Okay, these orbitals have nearly same energy and they undergo hybridization. They form hybrid orbitals of same energy. Okay, but 3s and 2p they cannot undergo hybridization. Okay, there are two conditions for hybridization. Okay, now let's see some characteristics. Number of hybrid orbitals found is exactly the same as the participating atomic orbitals. Okay, suppose if okay, if the participating orbitals are 1 2s, okay, and 2p. This is 2s and 2p. Okay, one okay, sorry. Okay, if it is like this, in at excited state, what it becomes? This electron shift to here.
Yes.
Okay, and it becomes like this 1s from. So what is this? 1s and 1p. Okay, participating orbitals are 1s and 1p. Okay, it is named as sp. Okay, the number of hybrid orbitals formed is exactly the same as the participating atomic orbitals. Okay, the participating is what? One one orbital of 2p and one orbital of s. The number of hybrid orbitals is 2. Is 1 sp and 1 sp. Okay, if participating of orbitals are from 1 s, from s is 1 and p is 2. Okay, so hybrid orbital become sp2. Okay, and if from 1s and 3p, it will become sp3.
Okay.
Okay.
And can you draw the this one for sp2?
Okay. Okay. In sp2, this is 2s and 2p.
2p, yes.
Okay. Okay.
Okay.
In excited state, it will become like okay. We'll shift here, shift here, and it becomes okay. It is sp2. Okay.
Yes.
And if it will be have it all the three orbitals of p, it will become sp3.
Yeah.
Okay. And always hybrid orbitals are oriented in space in such a way that there should be minimum repulsion.
Okay.
Minimum repulsion means more stability. Okay. For that, they are oriented in such a way that there will be minimum repulsion.
Okay.
Okay. We will see it in details. Okay. Types of hybridization. नौ बज गए आलम ऑफ कर दे आलम से बात कर रहे हैं सदर आलम सर आ रहे हैं क्या मैथ के ठीक है we will see one example of sp3 okay like in ch4 in ch4 carbon. What is the configuration of carbon? 1s2 2s2 2p2 ठीक है 1s2 2s2 2p2 we can show it in as a ground state in ground state ठीक है it is in the ground state okay 1s 2s and 2p then in excited state 9 to 10 what happens 1s is not participating in any bonding okay it is inner so, now what happened in excited state okay it will one of the s orbit electron will shift to the px py and pz okay now it is in excited state okay now in what in hybrid orbitals will be what will be the hybrid orbitals now intermixing between the orbitals of the s and p now they intermix okay and all of them become sp3 okay yes These all okay. This is the ground state, excited state, and now they become habit orbitals.
Yes.
Okay, with 1s and 3p. So it is called sp3. Okay, 1s 3p. Here what happens? One electron from the 2s orbital of the carbon atom is excited to the 2pz. Okay, orbital. Then the four orbitals are formed. Now four hybrid orbitals are formed. Okay. Each of these sp3 hybrid orbitals with one electrons overlap axially with what? Axially with one s orbital of the hydrogen atom. Okay? CH4. One each every unfilled orbital, a half filled orbital of carbon, okay, pairs with the hydrogen atom. Okay. And this way they will form the geometry tetrahedral. Okay. Okay. And the hybrid orbitals are always shown by the two lobes. Two lobes. Okay. Yes. One bigger lobe and one smaller lobe. Lobes means this is the lobe. Okay. Yes. This is what? This is the lobe. Okay. To have this, it shows the habit orbital. Means hybridization has done. Okay. If there is, it will show like a smaller lobe is actually it is not shown everywhere. So it is no need to show the smaller lobe. Okay. Okay. This is called, this is the tetrahedral structure. Although this structure is not very good, but this is tetrahedral, okay, geometry of sp3. This CH4 molecule. Okay, are you getting me? Yes. How the hybridization takes place in carbon and hydrogen. Okay, carbon was having 2s2 and 2p2. Okay, one of the electron from 2s orbital, okay, excited to the 2pz. Now it becomes four habit orbitals, all having the same energy now. Okay, all habit orbitals having the same energy, and this becomes sp3. And the geometry of the sp3 is tetrahedral. Now sp2 hybridization. You see the sp2 hybridization. Okay, this hybridization, sp2 hybridization, this hybridization involves the mixing of 1s and 2p orbitals. Okay, 1s and 2p. So how it will give three orbitals, habit orbitals, 1s and 2p, means sp2, sp2, sp2. Okay, three habit orbitals of all having the same or equivalent energy. Okay, let's take example of BF3. Electronic configuration of boron is
1s2, 2s2, 2p1.
Yes. 2s 1s2 2s2 2p1. Okay, and here we have three fluorine atoms. Three fluorine atoms. In ground state, we will show the configuration like one is we not necessary to show, not needed. Okay, I will show the 2s and 2p. 2s and 2p. In static state, what will happen? In static state, okay, one of the electron of s orbital shift to the p. This is px, py, and pz. So 2py orbital. Okay, so we can show like this. Okay. Yes. Now, what are the hybrid orbitals here? Hybrid orbitals are 1s 2p from. Okay, it is known as sp2. Okay. It becomes sp2, right? Two orbitals from p and one orbital from s. They make a sp2. Okay, actually their name comes from their parent atom. Okay, so this is sp2. Now we have to make bond with the three fluorine atom. Okay, fluorine has one half filled orbital in pz. So all the three fluorine atoms will make bond with this one f atom, one boron. Okay? Are you getting me? Yes. This way they make the BF3. What will be the structure of BF3? Okay. BF3. This is the geometry of the BF3. Okay. An angle between this BF3 this two is 120 degree. Okay.
And it will be 3 pi bond.
Hmm?
It will be 3 sigma bond.
Three sigma bonds, yeah. 3 sigma bonds, no pi bond. Okay. The name is this is the triangular planar. Okay. This is example of sp2. Okay. Then
and this for fluorine, this s electron will share with this.
yes, all the thing. Okay. The three fluorine atom will make bond with the all the three sp2 orbitals. Okay, because
Question bank. Next